Cool. I gotta close that. Cool. Okay. Yep. We'll wait 1 minute and then I'll get things rolling.
Nice.
How's everyone doing? Excited for break? Yeah. Always.
Oh wait, there's other people in the room?
Yeah. It's a talk. There's people watching.
I didn't expect it. No, that's
Morrison,
not a
I want
slight.
you to tell me specifically about what you're doing at work.
No,
Specifically.
I didn't listen. No, I guess I just don't have a lot of confidence in my pull as an entertainer.
Gotcha. Yeah, I mean, I get that. Like sometimes like setting yourself up with like lower expectations makes it less stressful. Okay. I'm gonna intro you and then we will get started. Okay. Everything works fine. Okay. Hey everybody. Welcome to talk number 2 in the RF talk series. There will be more, so make sure you come back. My name is Elizabeth. I'm president of the Rose Tech Radio Club. You may know or you may not know that we have 2 radio clubs on campus. One is all about music and the exploration of music and kind of recording technologies. And the other one, which is the one I'm involved in, is involved in communications technologies, signal processing, building radios and antennas, all that kind of stuff. So we're happy to have you here today. And we have a really cool guest. This is Morrison, recent alum, recent member of the club alum. I guess you could put it like that. I'll let him introduce himself, but we're going to have a really interesting discussion today about electromagnetic attack. So if you were here last week, we learned a little bit about how signals share space with each other, but now we're going to learn about what happens when they fight. So, Morrison, take it away.
Yeah. As Elizabeth said, I am Morrison. Again, I guess not again, but thank you all for coming out and taking the first day of break to, or some time close.
First
day
hour,
break?
technically.
First hour of break?
Yeah.
First hour of break to hear me ramble on about EA. Thank y'all. So, oh, my button didn't work. There we go. Generally, what the kind of layout of this talk is going to be, first of all, we're going to start with the background, like who am I? What kind of are some foundational definitions for electromagnetic attack, or EA? And then further, what is kind of the context in which I'm presenting? Like, why would the organization I am part of care about this? Then we'll move on to introducing EA's foundation so we can get our feet on the ground, which then will help us in the next section where we talk about some of the novelties about actually analyzing EA. And then that will lead us into our second from last section, which will be the EA integrated architecture, which is just how we analyze it, the process we go through to come out with conclusions on what's happening in the environment, what is being put out into the world. And then some of the things that I am and the team I'm part of are working on to improve that chain. Then, as all good and bad presentations have, we will have the conclusion where basically I just summarize what I said before and restate the thesis. So let's get started. Who am I? As mentioned, I am Morrison Gardner. I am a Rose alum in class of 2024, where I majored in electrical and computer engineering with concentration in communication, minor in math. I believe it was 2023, but at some point I was the treasurer of the Rose Tech Radio Club. And currently I'm an EA analyst for the National Air and Space Intelligence Center. So I've mentioned this term, EA, electromagnetic attack, a little bit so far. So before we move on, let's define it, because I would hate for someone to come out of this talk and think we're talking about how a gaming company is messing with planes and the like. So basically, EA, electromagnetic attack, is the utilization of the electromagnetic spectrum to disrupt and deny a target's intended usage of said spectrum. You are transmitting out into the environment to prevent someone else from doing the same. Because this is definitionally adversarial, right? It has attack in the name, you are targeting something. There are some novelties when we analyze EA. For instance, EA is target dependent. You can get some information on what is going on when you just look at EA in isolation. However, that's not going to get you the full picture. So if you need to have a target to see what the signal is doing in relation to. Additionally, EA is where when someone is performing an electromagnetic attack, it is most likely going to be very directional. They're going to be using an antenna with a very directional gain, because you want to target the thing you want to attack and not everything else in the environment. Additionally, there is intentional obfuscation, which, again, because EA is a adversarial thing, you don't really want it to be easy to remove if you're designing it. So there is, people put things to make it intentionally confusing. Some of the methods that we look at, or will be looking at to kind of get around some of these novelties, are utilizing artificial intelligence and machine learning to very briefly just go through how that kind of applies to the integrated architecture at the near the end, to categorize and classify EA, and then also how we can get away from some of the novelties with a standardized modeling method, and how we can store that information and use it for testing equipment and such. So that's generally what EA is. As I said, some context of why the organization I'm part of, the National Air and Space Intelligence Center, or NASIC. NASIC is the U.S. Air Force's Service Intelligence Center, the nation's Air and Space Intelligence Center, and an operational wing of the Air Force's ISR enterprise. Basically, what that means is NASIC's mission is to discover and characterize air, space, missile, and cyber threats to enable operations and inform national defense. What I do is I work in GXSE, or the Electronic Warfare Flight, which we deal with signals in EA stuff. That's to summarize that. So moving on to kind of start into the introduction of EA. What is EA? As mentioned, it is target dependent. It needs a kind of a target because it's attacking something. So let's start by, I guess, talking about that. EA can attack anything that uses the electromagnetic spectrum. We like to break that up into 3 categories: the radar, communications, and navigation. So let's kind of talk about why we'd split these up in this way. First of all, we have radar. Radar, its goal is to identify something positioned in space. There's generally 3 metrics can look at to identify something's position. That be the angle, and it can do this by finding the angle transmitted a pulse at. The distance to the target from the radar, and it can just get that by return time of the pulse, and then also the velocity that the target is moving at relative to the radar. And this can be collected by Doppler shift. That's just a change in frequency from the sent out signal. These are things that when EA is targeting radar, that it will attack, that it will try to disable or discombobulate. This is different from communication navigations because radar is less focused on transmitting information through space, but it's more measuring something from the environment. So when EA is being performed on comms, we have to worry about, well, when EA is being made to attack comms, it has to, one of the things that it has to determine is what type of information is being transmitted, right? Are we doing digital, analog? Are we doing, is this communication channel using just binary, some sort of binary sequence that's putting out the packets, or is it doing like analog voice? Additionally, when EA is targeting communications, it has to worry about, it has to, another kind of aspect it can play with is how the data is encoded. So if we're using digital information, depending on how the communications is encoding, so is it representing data in changes in phase, changes in frequency, or changes in amplitude, that will determine how the EA can attack the communications that's being put in the environment. Additionally, as kind of a subset of communications, we have navigations. We like to break this out into its own category because it's a large enough it's large enough utilized that it can kind of be its own thing. But basically, this is just getting the location. Most often, this is through sending a packet with timing information and identification, so stuff like GPS and that. So if we want to attack a target, what are the ways we can interfere with the electromagnetic spectrum to disrupt its usage? We kind of mentioned the targets, but how do we actually affect them? Well, a universal and simple method is to yell as louder than the target's transmitting, thus increasing basically the noise power. That's an easy way to cause interference in all three of these communications. If you just send more power into the environment than they are transmitting at, they won't be able to talk as efficiently. Now, kind of narrowing back down to the individual categories, we have radar. As mentioned before, the way that we calculate distance with the radar is through the time it takes a pulse to return back to our receiver. So if we want to perform an electromagnetic attack on a radar, if we receive that we have been targeted, we can add some time-delayed pulses to basically make this radar think, oh, it will get a pulse that takes a slightly longer time to return, so it might think, oh, there's something a little bit further away. Additionally, we can do a similar thing with velocity, where we, instead of adding a time delay, we can add a phase or a frequency offset, thus kind of mimicking a Doppler shift of some kind. Moving back to communications navigations, because they are carrying information rather than measuring from the channel themselves, we can also try to attack that information. And instead of just increasing noise power, there's other methods in which you can increase the bit error rate or block error rate to make the probability of error or the error of a packet much higher. Additionally, we don't just have to confuse and disorientate the communications or navigations targets. Instead, we can also add false information to confuse them, adding stuff that would make them do something that was not initially intended or something of that kind. So we've introduced a slew of methods that EA can use to cause interference with a target's intended function. But to generalize these, we like to group them into another group of three. First, we have denial and obfuscation. Denial and obfuscation is one of the simpler methods. Let's say you transmit something at a certain frequency. You have a bandwidth, you have a certain amount of power. If I want to make sure this is not received, what I can do is just transmit over it. This is decreasing the SNR and preventing something from possibly being successfully received or decoded when it is collected. So in the time domain, if you're sending out pulses, I could just continuously transmit and interfere. This is a very simple method. In fact, it's so simple that a lot of people tend to unintentionally perform denial and obfuscation EA. But if I don't just want to drown someone out, is there a way in which I could kind of augment this to add another layer of confusion? Well, if I, instead of transmitting a continuous pulse, I break this out into individual pulses, or continuous signal, just a bunch of energy for a long period of time, and break this up into individual pulses, I get another method, which we call disruption EA. Disruption EA, basically when the thing that will perform EA receives these pulses, what it will do is it will first transmit them back at a slightly higher power. What this does is for instance, with a radar, because we're listening for that return, what this tries to do is drown out that initial, the intended return, so that when we start transmitting more packets or more pulses, we can effectively confuse the receiver by making it lock onto our pulses instead of whatever it was looking for initially. Disruption's main goal is confusion, right? Again, going back to radar, this creates a bunch of false range targets because we're adding pulses at different time delays. Initially, this doesn't just have to be pulses. This can be some header for a communications packet so that whenever it's transmitted, the receiver just thinks something was transmitted without any data, and the channel is continuously used. Well, this is good for confusion, but what if we want to actively inject false information? Well, then we get something we call deception and spoofing. Let's say you are standing there. You have a friend and someone who's not a friend. Your friend, whenever they talk to you, they have a specific voice. In more of a electrical sense, that would probably be if a packet had a specific identification or something of that kind. Whenever they talk to you, they send out a packet, and it is identifiable by you as theirs. Let's say it's a green star. You know, this is a friend. But let's say you're not a friend. Whoever they are, whatever they are. When they could communicate with you in a normal fashion with a different identification stating that they are who they say they are, a red triangle. You don't know who that is. But instead of that, they can take some part of your friend's message, so whether that be just the identification or copying the whole transmit or parts of it, and they can either replay that or transmit that back out into the environment, making you think that their transmit is from a friendly. Some things that we see do this are something called digital RF memory, or DRFMs. These are effectively a copy and paste for the RF spectrum over a certain bandwidth. They're both commonly used in this one and the previous form VA. So we've seen the general three categories. Let's look at some examples. So let's start off with two examples from the natural world, because it's fun to talk about nature for a little bit. As some of you have probably seen or heard, bats are cool. They basically are little living radar things. They use sound waves, high-frequency sound waves that they produce to send out the environment and hunt for things in low-light environments. Some species of moths, which bats hunt, have developed abilities to counter this these pulses. Some of the moths have developed to be extra fluffy, which is, in kind of our EA schema, a form of passive, in air quotes, denial, where when the bat pulse hits the moth, it returns with significantly lower power. Additionally, other moths who already had sound-producing organs will produce clicks and chirps, which confuse the bat's pulses, making it easier for the moths to get away and harder for the bats to hunt. This, going back to the EA methods, would be probably a disruption EA. But bats aren't entirely helpless in this fight either, as it has been kind of seen in recent times that some of these bats that are hunting the moths that can produce sound are starting to change their frequencies outside of the moth sound producing range. Next, kind of on the border of humanity and nature, we have orcas and boats. So orcas also are a creature that use sound to hunt. However, it was noticed in the Pacific Northwest that orcas who were around boats had a significantly lower probability of success when hunting. This was because boats have motors, engines, a lot of machinery that add noise into the environment. These boats were effectively performing a denial or obfuscation EA on the whales, so as these whales would send out pings, they would decrease the signal to noise ratio and make it harder for them to detect their target. Now, moving back into human history, or more directly to human history and I guess war history, we have an example of EA used in our modern time, not real modern-ish times, in the Russo-Japanese War. So this war had a few interesting things. First of all, it was one of the first wars to use, to have widespread uses of radio communication to relay stuff to people. As such, it became important on both sides for them to have the enemy not able to talk. Well, what they found out was that by using a spark gap, they could transmit high bandwidth noise into the environment. If they pulsed it, it'd be very hard for the enemies to be able to communicate. Additionally, during this war, there was the first reported case of a radio intercept in the military world. What is radio intercept? Radio intercept is when, as the words imply, someone sends something out and a third party who's not intended to receive it picks up this intercept and can do what they will with it, whether that be use that intelligence for something else or further analyze it to kind of see what the capabilities are. Now, that leads us to how we pick up EA and some of the novelties for its analysis, because we still use basically we have to intercept EA to actually collect it. So EA is put into the environment. It's transmitted at something that wants to be attacked. Because this is directional, it's going to be very low noise when we receive it, and further, there are going to be more things in the environment that might overlay and overlap with EA. So now, some of you might be thinking, this is cool. It's hard to collect EA. Cool. But why are we staring at a blank screen? Well, throughout this presentation, I have been maybe very slightly performing my own bit of, maybe not EA, but interference on the slides. Some of you might have seen it, some of you might see it now, but in the background of almost every slide, there has been a large blue lobster. This lobster has been in every slide prior to this. Why am I bringing a large blue lobster into this? Well, just like it is hard to see that there was a large blue lobster in this slide, it's hard to see that there is EA in the environment. As I said, EA is it has very low power when we receive it. Additionally, there's going to be other things that we also have to pay attention to, and maybe things that even cover it up before we can see it. Thus, we have to look at the right place at the right time to actually capture EA. Additionally, even though we might look at the right place in the right time, we might miss a very valuable piece of information when analyzing EA, and that's the target. So you might be thinking, well, okay, we missed the target. We still know what the signal looks like. Well, here we see 3 different clicks of EA. We could say they look the same. We could say that these are all the same methods of EA, the same functions put out into the environment used to jam something. However, without the vital piece of information provided by the target, we can't say if they are acting the same way. So now let's say we have the target. Let's say each of these forms of EA is targeting these separate things. Well, we could say that the method of creation for this EA is the same, but we cannot say that the actual function of it is the same. So now that we've kind of seen some of the novelties, let's talk about how we analyze EA. So at a basic level, without the stuff that my team is working on, the way it is worked on is first, I like animations, they're lovely. Something is collected, EA is out in the environment, it's collected by us, where then, after it's collected, it is sent over to be categorized. Why does it have to be categorized? Because if we have EA that is known, that is already seen, or EA that is entirely new and unknown, those each have different methods that they need to be attacked by. So if EA is known, then it can be pushed on further to, instead of analyzing what the signal is doing, to see how it's in the environment, when it's active, and all that more abstract level stuff. However, if this collective EA, if this EA has not been seen before and is new, then we need to analyze it. We need to pull out each little pieces that it has and send that over to a database so that that can be transferred throughout the intelligence community, so that we're not the only people that have this information, but everyone has it. Well, there are two two problems with this current system. First of all is the categorization. Categorization is conducted by people. They do a great job. However, they are still prone to human error. And also, as people, they take time and have limited resources to look at one thing or the other. Their attention is being pulled in 1,000 different directions. Additionally, the types of databases that are used, or the way in which EA tends to be stored, is with parameters and text. So what that means is, if you are looking at some series of pulses, you'll say, what is the time between pulse? And then you'll give some information, and then you'll write a blurb about it. This is good. However, there is a problem with the written stuff with interpretation. And then additionally, there's another problem if we want to further do work on this data, if we want to simulate it or test equipment with this. So let's say I've collected a signal. This is it. It's a pulse signal with center frequency around yada, 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 big block of text. If I put this, store this, send it off, people will be able to know what I collected and maybe even develop their own models around it to test equipment, to show people what this is capable of. However, what would be better is if I just directly shared the models. So instead of collecting this and sharing a block of text with a few parameters, instead what we can do is we can share simulations and models to more effectively and efficiently convey information between groups of people and utilize that information more efficiently. So this is what that basically can be looking like so this is something called EAKB, or the EA knowledge base. The gears are spinning, yay. What the EA knowledge base allows us to do is, instead of storing parameters and text, we are storing simulations and models with some descriptions, so that you don't have to remake these models each time someone says, hey, I need a model. Additionally, this allows for these models which are shared to be uploaded to hardware so that equipment can be tested with stuff that has been seen in the actual environment that they will be deployed in. In fact, EAKB, out of the whole integrated EA architecture, is one of the things that is actively being used. The team that I own developed it, and it is currently in an initial stage where it's being tested and it is being put onto the environment. People are utilizing it, and it is actually helping to train and test things against real-world data. However, something else we can do with the AKB is, because we have these models, we can train AML models to identify new EA signals. So in the overall EA architecture, the whole analysis chain, the future work is more in that field. EAKB still needs to have some work done to it, but it is in a generally stable spot. The AML, that's the new thing that's kind of coming on the field, the buzzword in every aspect of everything nowadays. But basically what that does, and what the goal of that would be in this architecture, would be to utilize known characteristics of EA and the simulations and models provided by EAKB to identify known EA, and then using the models and simulations provided by EAKB, further train them on new EA that hasn't it hasn't been trained on before. Further, this would allow for EA to be more efficiently separated from the environment with its target, and also to have the ability to enhance categorization of EA. Because if you're not wasting a bunch of time trying to recategorize things that have already been categorized into known EA, then you can spend your time looking at the new novel things. So, in conclusion, EA is an electromagnetic attack, which it utilizes the electromagnetic spectrum to disrupt and deny a target's intended use of the said spectrum. There are some novelties around it, as we've seen, and then also some ways that we can get around some of those novelties and address them are standardized modeling methods and some AML methods. Some of the novelties, again, EA is rather rare to collect, whether this just be the collection's missed, it's too low power, or there's a low probability of intercept. What that means is, are we looking in the right place? Is the EA just targeting one thing and we're collecting miles away? Additionally, there's intentional obfuscation of EA. There can be added noise, pseudorandom frequency hopping, much more. And this all depends also on the target, because EA has to target something. If the target is really, really complicated, constantly jumping between different frequencies, then the EA is probably going to have to do that too. But we also need a target to determine that. So lastly, we know kind of some of the future work that we're moving towards is the implementation of AIML models, which will be used to separate known and unknown EA from captures. Some of the stuff that's currently been implemented and is being built on by my team is the standardization through EAKB, which uses models and simulations of EA to be stored and transferred. These models can then be used to further train AIML models and then also test and evaluate hardware against real-world systems. Currently, EAKB, again, is being used and supports around $500 million of DoD aircraft testing, which is really cool. And as it develops, it will probably be used in a wider aspect of stuff. So, any questions? Here's my contact information if you want to contact me. Yeah.
Thank you, Morrison. This is crazy. Okay, let's for sure field some questions. I'm gonna try to have people speak, and we'll see if you can hear them. And if you can't, then I will relay them to you. Okay, cool. Does anyone have any questions for Morrison about EA? Okay, we'll go here first.
I could not hear a thing.
You could not hear it. Okay. The question was, do you think EAs can interfere with satellite communication, and have you encountered that before?
So, EA, again, it can affect anything that is in the, it can affect any communication that uses the electromagnetic spectrum, right? So if someone wanted to, jamming is another word for EA. But if someone wanted to perform EA on satellite communication, they could. Again, with the navigation stuff, a lot of navigation used today is GPS, and GPS is, well, satellites.
Cool. Did that answer your question? Cool. Awesome. EJ, do you still have a question? Yeah. What's up?
Is it possible to use EA to physically damage a target, like burning the radar target?
Okay. So the question was, can you use EA to physically damage a target, like burning the target?
So it's not you can't necessarily physically burn. Like, you're not going to provide enough energy to provide radiation burns. However, when there are some types of EA, specifically with the denial or obfuscation EA, where if your goal is just to transmit a bunch of power into the environment, it is not unreasonable to blow out some more sensitive receiving equipment.
Yeah, that makes sense. Cool.
Mm-hmm.
Interesting. Yeah, some sensitive receivers with not as good amplifiers, maybe that wouldn't go so well. Cool. Okay. Anyone else in the audience have a question? Yeah. Got it. Okay. So the question was, what are some of the time scales for the signals that you're trying to classify with the AI models?
So the I'm not sure if I can give exact numbers, because
Classic.
I also I don't
Right.
I've not been playing with the AI stuff myself. That's
I thought it was going to be a government secrets thing.
but I most often I we're going to be looking at radar stuff, and we're going to be dealing with if we are depends really on the specific target, again, because some are going to, like, they're not really going to change in a matter of like 30 seconds. Some are not going to change in a matter of like microseconds, kind of deal. If that makes some amount of sense.
Does that illuminate it a little bit? Okay, cool. Anybody else in the audience? Yes.
Spoofing attacks. If we already have an EA that successfully like mimics whatever form of communication you're using, it's already infiltrated that system. How do you then detect it as something that's not supposed to be there?
Okay. That was a multi-layered question. Would you mind
Mhm.
coming up just so I don't mess up your just so I put it I don't put it in the wrong words. That's an interesting one.
I heard the last bit of it.
Yes, we'll make sure you get the full bit of it.
Mhm.
Hello. Yeah, I'm just kind of curious. Like when you talked about spoofing attacks, if you do have an EA that has successfully managed to infiltrate your communication, like it has successfully passed itself off as part of your communication system, how do you then determine that it's like a foreign entity that's not supposed to be there?
Well, so there it, again, depends on the target, but for something like, let's say GPS spoofing, right? That's the goal. That is saying you're actually here, but let's make you think you're over there. A way to identify that would be if suddenly you are in a different location than you were a short time ago. So navigation spoofing can have stuff like that. For communications, the actual by analyzing the packets, it's a little bit harder. The I can't give a clear answer on that. Yeah, but for stuff like navigation, it would be if you're not in the same place as you were previously, or if you're utilizing other sorts of stuff than GPS to kind of identify where you were previously. So a real good way around that is not relying on a single method of communication. So if you're using one specific type of communication and that is spoofed, then or well, I guess another example of this, you might be familiar with the roll jam attack on like car fobs, where basically you can prevent your using car fobs, you can intercept what they're sending out and then prevent the car from receiving that from the car fob and then unlock cars. Ways that some people have tried to get around this are by basically encrypting the packet with timing information as well. So whenever the packet is sent out, it's not only sent out with like a specific code. Let's say it's a pseudo random sequence that's just going to repeat every so often, like every 1,000 years or whatever. It's not just that, but it's also like Zord with the time. That is a way to probably identify, because then if you send it back, it's going to be a different time.
Mm-hmm. Cool. All right. I have two quick questions. Okay, the first one is I already forgot the name, the database of signals you were speaking about.
Mm-hmm.
Is it just shared within the US military? Is it like with allies? Is it just kept at your site? Like how is it used when it's shared?
So it is shared amongst the intelligence community.
I
Basically,
think that's where my question was.
yeah.
What defines the intelligence community?
Basically, that is NASIC and NASIC's partners, to speak generally.
Okay, I hear you.
Mhm.
Cool. And question number 2, is the lobster in the room with us right now on this slide?
Oh, hang on.
Because I
I
think it is,
I
but I
think
want to be sure.
it is. Yeah, it is.
Excellent.
It's the final lobster.
The final lobster.
Mhm.
Beautiful. Okay, awesome. Well, Morrison, I think that's it for today. Thanks so much for
Yeah.
hanging out with us and telling us about what you're working on. This is super cool.
It was a blast to come out and share what I'm doing.
All right, cool. All right, I'll follow up with you later.
Yep.
Everybody, if you have questions for Morrison, definitely take a pic and get in touch. If you have questions about the club or you have ideas for talks and things you want to look about, or excuse me, things you want to learn about, feel free to contact me. Yeah. Okay, cool. Thanks, Morrison. See ya.
See ya.
Now it's just me on the screen. How awkward. Okay, come on, mouse. Come on.